Poi Antonio ci togli una volta che abbiamo parlato, ci togli dal palco e lasciamo
Siamo,
il palco
siamo
libero
partiti.
a Fabrizio. Ok, siamo partiti e invito Andrea Orlandini a introdurre, ma non lo vedo.
Dovrebbe
Allora,
essere.
eccolo,
Eccoci.
ecco. Vai Andrea.
Grazie Luciano, buongiorno a tutti, anzi dovrei dire buon pomeriggio. Mi fa molto piacere avviare questo primo seminario del nuovo ciclo di Spotlight Seminar dell'associazione edizione primaverile. Ringrazio in particolar modo Luciano Serafini, Giuseppe De Giacomo e Antonio Lieto per l'organizzazione e poi ovviamente ringrazio Fabrizio Silvestri per aver accettato di appunto aprire questa prima serie della primavera. E come prima diciamo, uscita pubblica da presidente dell'associazione sono effettivamente contento perché appunto riprendiamo questa tradizione e spero poi come associazione abbiamo sempre più seguito. Sicuramente il seminario di oggi sarà interessante, i prossimi, e lascio la parola adesso a Giuseppe De Giacomo per introdurre lo speaker. Grazie mille a tutti.
Okay, I would switch to English, and it's a pleasure for me to introduce Fabrizio Silvestri, a colleague of mine, full professor of computer engineering at Sapienza University of Rome, where he also coordinates the PhD program in data science at our Department of Computer Control and Management Engineering. Fabrizio's research lies in artificial intelligence, with particular focus on machine learning, applied to web search, natural language processing. Over the course of his career, he has authored very many publications in leading international journals and conferences, industrial patents, which is a little bit strange for us academic, and received several awards, best paper, test of time. Before joining Sapienza, Fabrizio spent 8 years in industrial research, first at Yahoo and then at Facebook. And at Facebook AI, he led the team that developed AI techniques to detect and mitigate malicious activities on platform, including misinformation, hate speech, and other harmful behavior. He holds a PhD in computer science from the University of Pisa. And it has a very special character because Fabrizio's career bridges a little bit foundational research and large-scale real-world application coming from industry, obviously. So please join me in welcoming Professor Fabrizio Silvestri.
Thank you very much. Thank you, Giuseppe.
Fabrizio, it's your turn.
Yeah. Can you hear me?
We cannot hear you.
Yes, we can hear.
Okay. Okay, so apparently you can hear me. All right, so thank you, Giuseppe, for the kind introduction, and thank you to Aiperia for the very, very kind invitation. I'm very, very happy to be here. Today, we are going to actually look at some works that we have developed in these last couple of years, well, last year mainly, and on a topic that is, is not really, at least this rarely happens. It's not on large language models or something like that. It's mostly on graphs and how we can deal with graph-based data. So there is one thing that is kind of known, and it's a sort of, I would say, legend now. And the legend is that when you apply graph neural networks to graph-based data, you are let's say, making an underlying assumption, which is the homophily assumption. So neighbors are usually similar each other's. So you see there some examples of traditional graph neural networks and let's say why they enforce these assumptions that neighbors are similar. So in our case, and in the case of the structure that we are going to look at today, we replace similarity, so this similarity among nodes, with structural consistency. So we align the neighbors through learnable transformations. And these, as we'll see, changes everything. So these are the three failure modes that usually, let's say, you incur when you apply graph neural networks. Heterophily, so as I said, nodes might actually be different. It's not, let's say, if I am, let's say, from Tuscany, not all of the people I'm connected to, or all of my friends, are from Tuscany. Many of them are not. Another one is that typically graphs are also characterized by directionality. And typically, GNNs are not really well designed for this kind of situation. And then finally, higher order, let's say, structures like hypergraphs or more topological structures are usually not very well, let's say, designed. Are not very well suitable for being applied graph neural network to. So, as the title says, we are going to review some practical and some theoretical applications of Schiff neural networks. So before going on, I think it's good to actually introduce to everyone what a sheaf is. Sheaf or sheaves, let's say, are a structure that is inherited from mathematics, and in particular from algebraic geometry, where they are used to study structures on, let's say, that are made up of structures that are in the form of rings. So you have a well-defined structure attached to points in a topology. Now, we transpose this structure to graphs, as we'll see in a second, but what is an interpretation that you can give about this kind of structure? So imagine you are in a committee, and in this committee, each member speaks a different language, okay? So if you look at what a member of the committee says with respect to another one, you cannot really understand if there is an agreement or not, because there is this impedance, which is the different language. But what can you do? Well, you can introduce translators, right? And so now what a person or a member of the committee says, let's say, can be transmitted, can be transferred to the other committees by means of these translators. So essentially, this is, let's say, in explain me like I'm 5 terms what a sheaf is. In particular, you have a local knowledge, a local view, which is the view you have in your own language, and then you have, let's say, an edge that instead of being just a connection, the edge carries a structure that allows the translation from one language to the other. So by means of this edge, you can actually understand each other's. And this is very important. So we can translate these into mathematical forms, as you can see here. So we are in the graph realm, and now for each node of the graph, you attach a structure that is essentially a vector space, which is called stalk. So it's a vector space in d dimensions. And here is already the difference with respect to traditional GNNs, because in traditional GNNs, each node is represented by a single vector in a global vector space. Here, you have your own vector space local to a node. And now the translator, to, let's say, continue the parallel with the examples is a restriction map, which is a linear transformation that goes from the space, the vector space of the node V, into another vector space, which is the vector space of the edge connecting, let's say, V to another node. So here you essentially assume you know which nodes, which edge represent the connection, and on that edge you have essentially two vector spaces or restriction maps, two, let's say, linear transformations, one that goes from V to E, and the other one that goes from the other end, say U to V. Now, this is like the formal thing, and then an additional, let's say, property is the, let's say, consistency of a sheaf. A sheaf is consistent whenever the two linear maps on the edge, on each edge, are the same. So essentially, you have kind of synchronized the two sheaves. Now, there is another concept to essentially introduce here, which is the Schiff-Dirichlet energy. So essentially, it's an energy function, as in many examples of machine learning algorithms, that, if it's minimized, it means that if it's minimal, let's say, it means that the overall, let's say, the overall sheaf neural network, the sheaf applied to the overall graph, is consistent. The function is quite simple. Essentially, it measures the distance, the L2 distance between, let's say, the projection of the node linear transformation, the node vector space through the linear transformation from U through the edge E, minus the other way around, the linear transformation of V through the edge E. So when these two things, when this difference is minimized, your let's say, signal is globally consistent, globally in terms of graph. With this energy, then you can do as it is traditionally done, define the sheaf Laplacian. I don't know if you are aware or not, but a Laplacian is an operator. It's used, for instance, in differential equations, like in the heat differential equation, to define the diffusion process of heat. And essentially, when you apply the sheaf Laplacian, let's say you can build higher order diffusions that takes into account, let's say, the characteristics of each node sheaves. Now, this is very interesting because, again, once you have this sheaf Laplacian, you can do many things. For instance, the sheaf Laplacian is equivalent to the graph Laplacian whenever the, let's say, restriction map is the identity. So there is no restriction map. When you make the sheaf Laplacian learnable, as we'll see, you obtain a learnable diffusion process. So you adapt the diffusion process to your topology. And then, essentially, if you enforce globally consistent signals, you have a rich set of kernels for the signals defined on the graph. So differently from graph diffusion, you can think of graph diffusion as a heat diffusion process. And you can experience even physically when you place a heat source on a, say, metal plate, at some point after a while, the whole plate becomes uniformly, let's say, the temperature is uniform. So when you translate this into, let's say, graph terms, essentially it means that all the nodes are represented by the same representation. This is called also over-smoothing in GNNs. And instead, it can be proved that if you apply sheaf diffusion to graphs, this is not the case, because you keep the consistency of the local characteristics, and at the same time, you learn from the neighborhood, but only keeping, let's say, the compatible nodes, let's say. So your diffusion process respects the characteristics of the edges in this case. Okay? So this is the roadmap of the talk. I've already introduced what are sheaves and what they buy us. And then in the next, let's say, portion of the talk, I will essentially present two applications and two extensions, theoretical extensions of sheaves to hypergraphs and directional hypergraphs. So stay with me for the next minutes to see what we have done. So we'll start with an application of sheaf neural networks to recommender systems. I mean, you all know what a recommender system is because you are all buyers of Amazon goods or other things like Netflix or all that things. And so you know that especially in many real-world recommender systems, usually users and items are represented as nodes in a bipartite graph. So you have a bipartite graph where there are user nodes, item nodes, and then there are the observed interactions, which is the set R here. You have standard pipelines, Light GCN and GCF, Ultra GCN. All of them are pipelines that allow the building of a model that will enable, let's say, outputting recommendations to users. So in the standard pipeline, though, there is one caveat. Usually, your GNN considers, as I said at the beginning, each item and user as a vector in a global vector space. So it's a global vector space for the whole graph. Now, if you think about it, if I am the same user, right? But I'm not the same user when I interact with an item, say a book, or I interact, say, with a DVD. So even if I am a single user, I am different because whenever I interact with these two different types of objects, because of course, each object has different characteristics, right? So in order to capture these differences, right, we have to move to a richer space, okay? So this is why we moved to sheaf for rec, which is essentially, I would say, an extension or a globalization of popular GNN models, but to the space of sheaves. So in this case, naturally, each user or item are stalks, so essentially small vector spaces. And we have already a difference because at this point, you can actually have several, let's say, several characteristics of a user, right? And then for each observed edge, so whenever a user buys or interacts with something, you now, let's say, project, or better say, restrict the user representation to, let's say, to the edge, which means you try to capture the characteristic of the interaction itself, okay? So now, at this point, the prediction is done how? Well, you first take the user vector space and the item vector space. In traditional GNNs, you would simply do the dot product between xu and xi, because these are two vectors. In this case, they are not two vectors. So what you do, you have to project this vector into, using the linear transformation into the, let's say, the latent space learned on the edge, and then you can take the dot product. Okay, so essentially, as you can see here, you are adding an additional transformation that consists in, okay, let's extract the important bit of information from the user stalk and the item stalk. Okay, this is very, very important. I hope that by the end of the talk, you will be convinced that this is actually the kind of data structure you should use in your work whenever you deal with graphs or hypergraphs. And okay, architecturally is pretty simple. you learn the the restriction maps, as I was saying, and then you add n layers of shift diffusion, as you do in GNNs, except now, you learn both the user stocks and the restriction map. At inference, you just compute the restricted inner product for every user item pair, and then let's say the higher the dot product, the more let's say relevant is that item to the user. There is let's say there is this parameterization that I was saying. So you are restricting your restriction map to be diagonal. Diagonal means essentially that the restriction map is not a matrix, but is a set of numbers, which are the numbers on the diagonal of the matrix. So these are the results. And well, again, I don't want to spend too much time, but the numbers speaks by themselves. So let's consider NDCG. So as you can see, all the competitors, these are all, let's say, the state-of-the-art techniques. All the competitors are lower in terms of NDCG at 10. Consistently, we have other examples, but you can totally, I mean, the results are consistent, and this is repeated also on larger datasets like MovieLens, larger MovieLens datasets. And also, let's say, since Schiff neural networks are so powerful in terms of expressive power, you can essentially reduce also the time spent to compute, at inference time. So we observed a reduction in 25% to 37% in terms of runtime, and this is good as well. So these are the takeaways. I mean, a user is not one vector. It's actually a vector space. So the restriction map is the real thing that actually matters in this case. And faster and more accurate than strong GNN baseline. And okay, in this case, let's say the abstraction is orthogonal. We use the BPR as the loss, but you can use other self-supervised loss as well. So the second application is called Canvas. It's a paper under submission currently, and this has been done with two PhD students, Antonio and Ludovica. And essentially, Ludovica is doing an interesting PhD on AI and art in Zurich, and she came up with this idea that it's not, I mean, if you want to find a way to retrieve, say, imagine you want to retrieve all the masterpieces matching a textual description, right? So now the thing that you usually do in practice is to use CLIP. CLIP is a popular method to build representations of text aligned with the images. In this case, would be paintings. And the idea is that instead of aligning as you do using a vector for each, let's say, painting, we wanted to learn an alignment that is indeed, let's say, embedded into a Schiff space. And why is that? You would have understood now that relationships, when you have rich relationships, in that case, Schiff thrives. And here, what you do is what you need is exactly that, because let's say there are different relations between objects. There is style, iconography, historical period, artist, genre, date, material, and whatever. You don't know those characteristics in advance. So otherwise you could use multiple edges. But you know that depending on the text and depending on the pairs, you have some, let's say, interesting relationships and some interesting characteristics of the relationships. So we added that to, let's say, to CLIP, essentially. And this is, let's say, a Schiff-informed contrastive learning. So we don't have labels here. It's a self-supervised method of doing that. Why it is sheaf informed and not really sheaves? Well, because instead of having, let's say, the whole graph built, here we essentially exploit just the pair, of text and image. But at the same time, once we embed them in a vector, then we lift this vector to a vector space, and then we compute, and then we learn a restriction map, different restriction maps for each pair. And the number of restriction maps is essentially the parameter that controls how many relations you learn. And then, you combine these relations as well. So it's graph-free, essentially. In this work, we actually added, and this is another interesting contribution, 2 novel datasets. Novel in the sense that these datasets have never been published, never been released to the public. And this is important because they are not known, they are not being released to the public. They've also not been used to train CLIP. So it's kind of out of distribution for that. And so here you can totally and really see the added value of sheaf neural networks. We also use the SEMART, which is an existing data set that we essentially enriched to be used with sheaves. So Hertziana and WikiArt are 2 new data sets, okay? And as you can see, we had essentially 2 tasks defined on these data sets. One is a popular retrieval task. So you insert a text and you want to retrieve all the images that are matching the text. And then another one is like relation-wise classification. So you take, let's say, 2 paintings and you want to detect whether they have been painted by the same artist or they are from the same period, or, you can see that. And so if you look at the text-to-image task, the recall at 10, which is what is useful in this case, it's much, much better when you use sheaves with respect to, let's say, traditional embedding mechanisms. So again, our Canvas method is an embedding method, is the same as CLIP and whatever, but it enriches these with the relationships that might arise from this kind of domain. As a side note, we also tested these in other domains, and Canvas is always, let's say, as good or even better than traditional embeddings. So you should replace your text image embedding with Canvas if you want to have a higher precision. And the same you observed in the case of classification accuracy. I didn't put the competitors because, let's say, they were all worse or more or less the same than these. And as you can see, for particular types of relationships, we are always the best. So what are the takeaways of this method? Well, multi-relational structure is the norm. So especially in culturally rich domains. So, especially when you have to deal with, let's say, images coming from, like work of arts or stuff like that, you need to consider different aspects. But it's also true for, let's say, in general, for, texts. You have text from the same author, different periods, same periods, and whatever. And then one interesting thing is that this technique is just lightweight. That is, you don't really need to add or to retrain CLIP. I didn't mention it. So you don't need to retrain these 2 things. As you can see here, CLIP is frozen, so you don't retrain them. So you only train the restriction maps, which are essentially learned. And this is a very strong point of the technique. So it's adaptable. You can take your favorite embedding mechanism and you will get an improvement. And it's also graph-free at inference. So you assume you have a graph, but at inference time, you don't need a graph. You just need to build the embedding through the restriction maps that you have learned. All right, so let's move to the third part. So now we are starting with a more theoretical part. So this is, let's say, Schiff neural networks, but applied to hypergraphs. This is a joint work with Julia Duta and Julia. Both of them were PhD students. The first one at Cambridge, the second one at Sapienza, and then I and Pietro Liò were the co-advisors of them, and this has been published at NeurIPS 2023, so 2 years and some months ago. And we extend Schiff neural networks to hypergraphs. And, you know, an hypergraph is essentially a sort of lift or generalization of a graph where you have not just 2 nodes involved in an edge, but more nodes involved in a hyperedge. So how do you see this structure as a let's say that can be treated by Schiffs? Well, essentially you consider each hypergraph as a sort of hypernode, let's say, and then if 2 hyperedges share one node, then you kind of have an edge between the 2. So with this, you could just already build the extension to Schiff-NN. And in fact, this is what we did. So we have one stalk, so one vector space per hyperedge, and one restriction map per incidence. So it's, I mean, you just need this, let's say, you know, mapping between graphs and hypergraphs, and you have the same thing. Now, how do you build consistency? Let's say, so in this case, so whenever a node is part of an edge, you have a restriction map. So you see that already in many, this is also another difference, in many GNNs or that are designed for hypergraphs, you lose this, let's say, this property of having different roles played by different nodes in the same hyperedge. And in this case, instead, since you learn a restriction map between a node and an hyperedge, you are kind of, you know, fostering diversity. And also global consistency now is replaced by consistency on a hyperedge that essentially is when you have the same restriction map, the restriction maps agreeing for all the nodes in an hyperedge. So we proposed in this work 2 different Laplacians. And so once you have the Laplacian, you can essentially just reuse it in the in the typical diffusion mechanism for graphs. So for graphs. So we have a linear graph Schiff hypergraph Laplacian, which is very simple. You let's say you take the average of the differences between the restricted let's say vectors for each pairs of nodes in a hyperedge. So, and then you sum over all the hyperedges. Okay, so it's very, very simple. And this is it's called let's say linear Schiff hypergraph Laplacian. And we essentially proved in this paper that you know, Schiff diffusion, when you replace, let's say, diffusion with the typical diffusion with this Laplacian, it minimizes the Dirichlet energy, which means you find the optimum representations for the nodes in the hypergraph. And as in the other cases, whenever you use the identity in the restriction map, you recover the classical hypergraph Laplacian. Then we also defined a nonlinear version, and essentially here, instead of taking the average, you just want to minimize the max difference, which means essentially it's a nonlinear and it's more expressive. Also, the nonlinear variant minimizes the Schiff total variation, which essentially, let's say, dominates the minimization and dominates the diffusion as well. And why did we propose also the nonlinear variant? Because essentially we wanted to be robust to hyperedges where the content of each hyperedge was mixed. For instance, you have, I don't know, an hyperedge consisting of full professors or PhD students. Okay, so they are kind of let's say heterogeneous, and so you don't want to mix up things. Okay, and essentially this is the Schiff hypergraph network. It's what you would expect, especially after you see the presentation on the graph Schiff4Rec. But only, again, one thing that should be noted is that we tested several variants of the restriction maps. So we learned a full restriction map, so a full matrix, a full linear transformation. But then we also we simplified the learning by learning, as I said in Schiff4Rec, only diagonal linear transformations, and the difference is really minimal. And we went on with diagonal. Again, diagonal is learned by having the MLP learning the restriction map return just the values that are the numbers in the diagonal instead of the squared values. Again, we ran several experiments. First, we wanted to check in an heterophilic setting how this method worked. So alpha here, as you can see, let's say, kind of controls a fraction of hyperedges that are mixed up, so heterophilic. So the higher, the more heterophilic. And as you can see, when it's really heterophilic, other other GNN mechanisms start to fail, and instead Schiff hyper-GCN is stable. So it's insensitive, essentially. And this is instead also reflected in real-world node classification, where Schiff hypergraph, let's say hypergraph convolutional networks, is always winning or on par with the competitors. There is a mistake here. This shouldn't be bold, but anyway. So this is the takeaway. So Schiff's lift hypergraphs, as they let's say lift GNNs, and there are strong empirical gains. And so the real key takeaway should be use Schiff's GNNs also in the case of hypergraphs. Okay, so in this paper that has been done in collaborations with a lot of people from University of Bergamo, and then let's say other institutions, that has been published. I actually presented last week at ICLR 2026, extends the Schiff hypergraph networks to the, let's say, realm of directional hypergraphs. Directional hypergraphs are are more popular than it sounds, in the sense there are many domains where directions is important. For instance, in chemical reactions, you cannot go from H2O from H2NO2 simply as you do in the case of the other direction. And citations as well, workflows, email, sender versus recipient, and so on and so forth. So in some way, in Schiff hypergraph networks, let's say restriction maps are symmetric in V. So they are symmetric matrices. Each member essentially plays the same role. But in this case, we don't want symmetry, let's say, we don't want to foster, let's say, the restriction to be symmetric, because we want to, let's say, to capture the relationships, the relational direction. So what we did, let me actually move a little bit quicker. What we did is we added this term here, which is a phase modulation, to the restriction map. And as you can see here, it's basically we are making the restriction map complex. And as you can see, when you have a complex transformation, when you compute the dot product, essentially, by changing the order with which you compute the dot product, you switch the sign. And so, this kind of, let's say, complexification helps in capturing the direction as well. And in this case, we introduced, let's say, this parameter here, Q, which is learnable. And so we actually learn what's the importance of the direction. It's a sort of charge, okay? And it's interesting because depending on how you set the charge, you can recover several Laplacians, okay? So essentially, you have this parameter, which is a single real number that is actually learned during the learning of the restriction map. And so at this point, let's say the previous linear sheaf becomes, let's say normalized directed sheaf hypergraph Laplacian. And this is actually the unique Hermitian, so it's Hermitian. So as we'll see, this has a very interesting property. And I mean, it's a positive semi-definite operator that you can see here. So now the energy, as before, is x times the Laplacian, this Laplacian. Again, the fact that the Laplacian is Hermitian has several interesting properties, but the one that is really important is that it can be diagonalized with a real spectrum. And now we can actually compute the largest spectrum, which is at most 1. And this is actually helping because at that point you do not use the Laplacian anymore, because, I mean, it's a usual trick that is applied in graph convolution, for instance. You just replace, the spectrum with the maximum spectrum. So essentially, as I was saying, depending on the choice of Q, you recover several Laplacians. So if Q is greater than 0, when you have no, let's say, when you have one dimension, so no restriction, you recover the magnetic Laplacian from Zhang in 2021. So when D is equal to 1 but signed, so you recover what is called sign magnetic, that was proposed by one of the co-authors of this work in 2023. Then if Q is equal to 0, so if you don't use it, it's a hypergraph. And if Q is greater than or equal to 0 and D is greater or equal to 1, it's the unification of all of these. So the method learns from the data which Laplacian is best, because the Laplacian defines the restriction map. Also in this paper, we corrected a small, let's say, mistake, if you will, that we introduced in the previous paper that I showed you. So the previous paper, despite we called it Laplacian, it wasn't really Laplacian, the linear sheaf hypergraph Laplacian, because it wasn't positive semi-definite. So our, let's say, case, let's say with Q equal to 1 and D greater, Q equal to 0 and D greater than 1, it's the real actual linear sheaf hypergraph Laplacian, which is also positive semi-definite matrix. So this is the architecture. It's essentially the same as the previous one, just we change the Laplacian. And we try two different variants, the SHN, which is the full model, and then the SHN light, where Q, the charge, is 1 for all the various layers and nodes. Of course, in the classification, let's say, sorry, once you run inference, you get a complex number, a complex vector, you just take the real part before the classification. And this beats, in most of the cases, let's say, the GNN and the Schiff hyper GCN in most of the cases. And yeah, so in the case of directed graphs, you should really use these because it's actually state of the art. And also by looking at the directionality in the synthetic data set, as you can see, we are consistently better than the others. So we are kind of running out of time, but the takeaways here is that, complex valued restriction maps encode direction as expected. We actually proposed a new Hermitian positive state indefinite Laplacian with a bounded spectrum that can be used in the training, but also a small spectrum means that the deep message passing, when you stack several layers, the diffusion is well conditioned, and so it, let's say, it works. And then there are, let's say, empirical gains that are consistent in all directed, real-world directed hypergraphs. So there are several open challenges here. Scalability. So let's say we would like to make this method even more scalable than they are, because as you can imagine, we are introducing several additional parameters. So if you really, because now we are not dealing with a single vector, but with vector spaces, so we are, let's say, having a quadratic explosion. So in real world problems, the quadratic explosion is controllable because to get to the same level of accuracy, you need less layers. So it doesn't really change much. But if you want to scale this to several layers, we need to think of ways of scaling up these. And then we are now consistently trying to scale up beyond Laplacians. So we want to use sheaves in transformers. So this talk is LLM free, but the topics can be applied to LLMs as well. Neural ordinary differential equations, and then in chemical domains, equivariancy is a property that you want to enforce, and many other things. It has been released today, like some hours ago, by a colleague of ours, a paper on causal sheaves. So one of the challenges here has been addressed already. So I would like to thank also all the collaborators like Giulia Dutia, Giulia Cassarà, Pietro Liò, Emanuele Mule, Stefano Fiorini, Antonio Purificato, Federico Siciliano, Stefano Coniglio, and Ludovica Scherf. And also thank to all of you for the attention, and I hope this has given you a new tool in your toolkit to deal with graph-based problems. Thank you very much.
Thank you. Okay. Can you hear me?
Yes.
Okay. Thank you very much, Fabrizio. Very interesting presentation. I don't know, Giuseppe, do you want to manage the question, or should I do it? Just let me know. Okay. So no answer. I suppose I will do it. So let me start with an initial question. So, okay. So first of all, thank you for the presentation. I think it was, despite the complexity of the topic, for me at least, it was given in a very clear way. So all the difficult stuff were kind of hidden in
the paper.
the papers, exactly. So at first, maybe a stupid question, but when you speak about these transformations that you add in order to add more information on the links, it reminds me these attention layers that you have in a transformer, where you have the key and the query, which basically are transformation of embedding. Is there any relation to that? Or
So essentially, it's kind of equivalent when you, let's say, have, let's say, D equal to 1, and you have exactly the restriction map of dimension 1. Now, what is the difference? The real difference is that in the case of graph attention, you are, let's say, taking a vector, which is always the same, right? And weighting differently the dimensions of that vector. So you are not taking a vector space and picking the right vector among the infinite number of vectors you have. So it's a different thing in the sense that you don't, let's say, project a vector into a subspace. You take a vector space and you project and you find the best vector in a different vector space, which is the vector space of edges. So from a geometric perspective, it's totally different. So it's the transformation that selects the best vector and not the best dimensions from the node. So it's a sort of generalization to this.
Okay, thank you very much. And then I have a question that comes from my logic background. I know that graph neural networks are equivalent to the L2 logic, so the first order logic with two variables.
Okay.
Now, these extensions, Chef neural network, do you extend also the expressivity of graph neural network, or somehow from the expressivity point of view, you can go back to standard graph neural network?
So in the case of, let's say, traditional shift neural networks, I didn't do it, but let's say Chris Bodnar and others have proved, let's say, the expressivity of shift neural networks, which are, let's say, I would remember, okay, I go using my memory, which is not very good, but it's similar to those of graph neural networks in terms of expressivity. Because, you cannot really go beyond, well, I don't know if you can go beyond with these. So with these architectures, you cannot go beyond Westphaler-Lehmann tests or KWL tests and whatever. I'm not aware of any equivalence proof with respect to first order logic, with respect to SHIFT-NN. For sure, not for SHIFT hypergraphs. We didn't do any of that.
Okay, thank you. So it's you can add it to the list of the open problems.
It's actually a very interesting open problem indeed.
Yeah, to understand that the connection, if there is any connection with some, say, fragment of first order logic, which is a little bit larger than two variables first order logic.
Yeah. So in a way, you can think of a sheaf as a way. So imagine you have an algebraic structure, like a group or a topology, whatever. You take each point in this structure and you attach data. And so now you can imagine that this is very, very useful in machine learning, because it is what we do, except you lift these in a higher order, let's say, space, and you can manage more complicated relationships. So this is, let's say, the reason why I really like shifts in general.
Yeah. So here there is a message by Giuseppe, who for some reason he cannot hear you over the platform, but he listened to you over YouTube, and he congratulates for the presentation, was really nice and so on.
Thank you.
So I think I have a time for another question, and this is about. So at the beginning, I was particularly was particularly interested by the fact that you say we can have different embeddings, different size associated to different embeddings. Sorry, to different nodes.
Mhm.
So maybe one node you have, I don't know, R3 and the other node R20 and so on and so forth. So, but during the talk, I didn't get any point in where you say, here we use actually this feature. And this was really a key point.
Now,
Maybe I've missed something, okay?
my bad. No, my bad.
Okay.
We used the here. So user, let's say user representations were, let's say, 512 dimensionals, whereas item dimensions were 256. And in general, exactly. So in general, this is a feature you can only have with this kind of structure because eventually the representation is given by the matrix associated with the node and the restriction map. So you cannot build a single embedding out of them.
Yeah.
You always need the projection, the restriction map, which is a projection. But anyway.
Okay.
Yeah.
And I suppose it's an obvious observation, but maybe the more node you have for one type, then the larger the embedding for the node of that type, I suppose.
Yes. And so the rule of thumb is the more diverse the domain is. So for instance, users are much more than items, like user types are more than item types. And so for users, we need a richer representation. Okay. Well, this is at least empirically.
Yeah. Okay. But it's intuitive. It's very intuitive. So, okay, let me check if there is any other question. No. So I think it's time to close the seminar.
Before we close, 3 minutes. I just want to make a final remark, which is, I said at the beginning that this is an LLM-free presentation. I should have said an LLM-free talk, because in the presentation instead, as you can see, I used LLMs to draw all the pictures and the figures that you can see here. And so it's actually an LLM-free talk, not presentation.
It's not free. It's not so free. Okay. So thank you again, Fabrizio.
Thank you.
The talk will be online in the channel of AI-per-IA, and I'm sure that there will be many visualization. And I hope maybe you will have many feedback or useful feedback and reaction from the people even offline.
Yeah, and if someone wants to collaborate on this, you are more than welcome to get in touch.
Thank you very much.
Thank you.
Okay.
Thank you.
Okay, so it's time to closing. Bye to everybody. Thank you.